Good morning, everybody. I just wanted to make you a little video really quickly about how you can classify the different types of reactions. Yesterday you watched a little video about all of the very individual, very specific types of reactions, but there are actually two major classes of chemical reactions which they would belong to. They're called double replacement, which you should have covered yesterday, and then a large class of chemical reactions called redox reactions. So they're actually very easy to identify. Double replacement, its trademark is that it's really between two compounds on the reactant side. So anytime that you see compound plus compound, it's instantaneously a double replacement reaction. And I'm hoping that you saw on your notes page from yesterday that double replacement reactions essentially come in two flavors, precipitation or acid and base. And they're actually also pretty easy to tell the difference between. What I usually do is I look to see if I have an acid-base reaction. So when you're taking a look at your reactants, if you have an acid, you should have a compound that starts with H. A base is a compound that ends in OH. So if you have some H something plus something OH, that's an acid-base reaction. Now they will always form water, H2O. You can write that HOH. Remember how we kind of talked about how we can kind of cheat there with how water looks on the product side. And something called a soluble salt. The state symbol will always be AQ, and salt is more than just NaCl. It's any combination of two ions at all. Just neither acid nor base left over. So there shouldn't be an H in it. There's usually not an OH group left in it either. An example could be like potassium nitrate. That's considered to be a salt. Or lithium fluoride. That would be another example of a salt. The most important thing to remember is that if it is not acid-base reaction, it's instantly going to be considered to be a precipitation reaction. A precipitation reaction would be compound plus compound, and what you're going to do is when you're predicting those products, essentially the anion, the back end of those two compounds switch places. They switch partners, almost like a little do-si-do. When you're assigning the new state symbols, one of those new state symbols should be S, and one of those new state symbols should be AQ. The S labeled compound is called the precipitate. It is a solid that falls out of the solution. It almost looks like rain. We're going to play with those on Monday and Tuesday, depending on when your lab day is. They're actually really fun to kind of take a look at. So like I said, if it's not acid-base, it's almost instantly precipitation, and you have to be careful with that. Even though you might label it as being a precipitation reaction, if one of the compounds does not form a solid, no reaction occurs. So now we're starting to get to the ability of being able to predict whether or not these chemical reactions are actually going to take place in the first place. So for a precipitation reaction to actually create a chemical reaction, it has to form a solid. Last thing you need to know about double replacement reactions, the ions inside of them do not change charge. So if you were to assign the charges of all of the ions that are involved in a double replacement reaction, they stay exactly the same from the reactant side to the product side. I have an example later on that you can actually kind of see this in work. So that's double replacement reactions. Redox reactions. They're super easy to identify. You look at the reactants. If it's not compound plus compound, it's a redox reaction. And there are 4 subtypes of redox reactions. And we're going to play with a couple of those today. Specifically, you're going to look at synthesis and decomposition. Those are 2 types of redox reactions. The other 2 are single replacement. We'll look at that later on in the week. And you already met combustion reactions. They're not very mysterious. It's a carbon and hydrogen compound plus oxygen, and will always form carbon dioxide plus water. For right now, the most important thing you need to know about a redox reaction is that the elements inside of the compounds will change charge between the reactant and the product side. And like I said, we will have an example of that coming up here shortly. Okay, so let's say that I wanted to identify what major type of chemical reaction that I'm dealing with. Let's take a look at example 1. So we have sodium nitrate plus potassium oxide. So what I see here, sodium nitrate is a compound. Potassium oxide is a compound. So that's compound plus compound. That is instantaneously a double replacement reaction. Now you can start to take a look at the subtype, or what specific type of double replacement. Now remember, that's either acid-base or precipitation. So sodium nitrate, that doesn't start with hydrogen. It doesn't end with hydroxide. So it's neither an acid nor a base. That's a salt. Potassium oxide. Potassium, okay, so it doesn't start with hydrogen. Oxygen at the end of it, that's not hydroxide, so it also is neither acid nor base. This is not an acid-base reaction, so it must belong to precipitation. Now you start to go and assign your state symbols, and notice in this case, both of them end up being AQ. So guess what that means? When I put sodium nitrate and potassium oxide together inside of a chemical reaction, nothing happens. They're just going to sit there and kind of look at each other. It's very weird. So again, this is an example of a non-chemical reaction. Okay, let's take a look at example number 2. So we have iron plus oxygen. Instantly, what you should recognize, iron, that's not a compound, it's simply an element. And then we have oxygen, that's not a compound, even despite that little 2 at the bottom, it's still considered to be an element, because in order to be a compound, you need 2 different kinds of symbols next to each other. So that's element plus element. Well, that's not compound plus compound, so this has to belong to the major class of chemical reactions called redox. Redox stands for reduction and oxidation. Redox comes in 4 flavors. You have synthesis, which this chemical reaction is an example of. You have element plus element. You simply write down their 2 symbols, and then to predict the products, you smoosh those symbols together, predict the charges from the periodic table, crisscross to get your new compound, give it a good state symbol. Balance that reaction and you're good to go. Decomposition is the opposite of synthesis. So you'll be presented with 1 compound on the reactant side, and that's it. All you have to do to predict the products, rip the 2 elements apart, write them down, give them some state symbols. Balance the equation, you're good to go. Combustion, we've already talked about. And single replacement, we will start with early next week. But those are your 4 flavors of redox. So let's take a look more specifically at what this redox thing actually means, because this will pertain to your homework for over the weekend. Don't forget to check Google Classroom. I gave you some notes there as to what I'm expecting you to be able to get done today. Okay, so again, redox stands for reduction and oxidation. It's just kind of the shorthand version of saying all of those syllables. Reduction is specifically when an element on the reactant side to the product side seems to become more negative in charge. So it'll actually gain some electrons. Oxidation is when the element's charge becomes more positive, so it'll actually lose electrons. So the cool thing about a redox reaction is that electrons are actually jumping from element to element. And any time that you have an electric charge, an electron that's moving from one place to another, that's technically considered to be electricity. So you'll find that redox reactions are used frequently in place of like batteries. A lot of our chemical batteries employ redox reactions. And in fact, one of the things that we're going to be doing in the next week, we're going to build our own batteries using many different redox reactions. All right, so at any rate, let's take a look at a very specific example. Let's go back to this iron plus oxygen example, a synthesis reaction. And what we're going to need to do is identify what's oxidized and what's reduced. Okay, so things that you need to know. Elements that are written by themselves, whether they be solid, liquid, or gas, just by themselves, pure state, always are assigned a charge of 0. Elements that are inside of compounds, you can use the periodic table to be able to predict their charges. Now I know that you're saying to me, well, iron, I can't look at the periodic table and predict his charge. However, you are provided with the full chemical formula. You know the charge of that oxygen, and you can use that little algebra thing that we kind of went through together to kind of back calculate to what the charge of that iron must have been. A lot of the times you can find this from uncrisscrossing the compound, but be a little bit careful. Like in an example like SNO, when you uncrisscross that, you'd be uncrisscrossing ones. We would uncrisscross a 1 charge to the oxygen, but oxygen is a -2, so that doesn't make sense. Always make sure that you identify that negative charge inside of your compound first, and make sure that it actually makes sense when you uncriss-cross it. So here's what I did down below. If you notice up in the superscripts, I've actually assigned the charge of each element involved here. Iron in the reactant side has a charge of 0, again written by itself. O2, that's elemental oxygen, written by itself, charge of 0. And then inside of that compound, I was able to uncriss-cross it to get my charges back. The iron ions on the inside of Fe2O3 would have a positive 3 charge. The oxygens would have had a negative 2 charge. So what's happened here? Well, because the iron started off with a 0 charge on the reactant side and then increased to a positive 3 charge on the product side, we say that it was oxidized. And then with the oxygen on the reactant side, it starts off as 0 and then decreases down to a negative 2 charge. So we'll say that he was reduced. So again, check Google Classroom for your very specific assignment for your class. I will be back on Monday and we will go over everything in full detail. Thank you for your patience, and I will see you then.